Okay, so hi, my name is Doron Rosenberg. I work for IBM in a group called Emerging Technologies. I've been working professionally with JavaScript for about 15 years now. I'm here today to talk about one of our projects called EclairJS, which combines Node and the distributed computing powers of Apache Spark, which is very different from music. So there's two kind of trends, really, kind of in the more enterprisey world, right? Node is growing fast. A lot of people are using it. Growth is doubling roughly every year. A lot of companies are using it across all sizes and shapes. It's not just startups, but big companies like Walmart or IBM are using it. And another thing that all these companies share is that they're generating tons and tons of data. Access logs for your websites, your web services, transactional data, sales, et cetera, user actions you're monitoring, all that stuff generates data. And we find that very little of that data is actually ever analyzed in a meaningful manner. Usually you get a nice little pie chart telling you 25% of users come from the United States. That's roughly as deep as you go usually. But when we talk to companies and our customers, we find that they actually do want to go deeper into the data. They want to gain insight is usually a word they like to use. Like, let's analyze the data, learn something from our data. For example, if you're running a web service, you've got all these access logs. You might be able to look at those access logs and determine that, hey, 25% of my people who use resource A end up using resource B down the line. Well, that can become a recommendation engine, right? You can drive traffic to your application, to your web service, potentially gain more insight, maybe monetize that better. Might be a competitive advantage you can get from kind of looking at your data in more detail. Another example is the more traditional retail world. You've got a warehouse full of a product, and there's a new version coming out next month. What's the based on the historical data, what's the highest price I can set to clear out my inventory in time for the new release? Those are just two examples of what companies are looking at when they try to analyze their data and again go deeper into their data. But why aren't companies doing that? Well, the problem is that there's just too much data. You can't just process it on all. Sorry, I'm getting dry here. Sorry. There's so much data you can't process it on one machine in any efficient manner. So you have to go to distributed systems. People like to call it big data, which is a keyword for it. There's tons of data, gigabytes, terabytes, petabytes, and so forth. And so you have to go distributed computing, which is a pretty complicated thing to do. And one of the kind of the fastest growing distributed computing engines out there is Apache Spark. It describes itself as a fast and general engine for large-scale data processing. It originally came out of Berkeley, out of a laboratory called the AMP Lab, and it was contributed to the Apache project where it was open source. A bunch of companies are investing a lot of money into it. IBM itself has a Spark Technology Center down on Market. It's about, I think, 50 people working on it right now. A lot of companies are using it, selling it, and deploying it in their companies. Spark is a successor to some other technologies like Apache Hadoop. Its focus mainly is on improving performance, adding more feature sets, making it easier to use, and so forth. So on the feature sets wise, Spark has a common API for working with both static and streaming data. So you can use one set of APIs to work on data no matter which way it's coming in, right? Either statically from a file system or streaming from some sort of service. Spark also allows you to use SQL on big data. SQL is still around. It's highly popular. It's never going to go away probably. So, and people love it for some reason. So for better or for worse, Spark provides a SQL support, allowing you to use SQL to run on this big data, modify it, etc. Spark also has a rich set of machine learning APIs. This is a big new thing with data science. Basically, you take your existing data, you train a mathematical model using that data based around linear algebra. Fun stuff, I know. And then you can run predictions against that data. And I'll have a quick demo of how that looks. Hopefully the demo will run. Finally, Spark also has a built-in distributed graph engine called the GraphX. And like all systems, Spark works by having a master server you communicate with. It controls multiple worker nodes. And then those worker nodes have multiple worker processes where the actual data is being processed on them. This makes it highly scalable. You can have as many worker nodes as you can. Performance won't degrade. It's also fault tolerant. So if any of those nodes go away midway through a computation, Spark can recover gracefully for you. Importantly, it does that for you. You don't have to worry about any of this stuff. It's all automatically done for you by the scheduler that it comes with. So even though Spark is, again, designed to run in these big clusters of machines, it does come with a local mode, which runs everything, the master and the worker nodes all on one machine, like this Mac here. This is great for development. You can start working on your small data sets, iterate with your code. And once you're happy with your code, you can just change an IP address, and then you're working against a cluster of machines. Spark is built on top of the Java virtual machine and supports Java, Scala, R, and Python by default, but doesn't support JavaScript or Node. So this is where the EclairJS project comes in. EclairJS.org, we're on GitHub appropriately. And the goal is to provide Node developers access to Spark and its APIs. We implement the APIs one-to-one for Node developers. Again, we're fully open source, Apache 2 licensed, etc. EclairJS is composed of two pieces. There's the client piece, which is an NPM module. And then there's a server piece, which is a kind of a lightweight piece that sits where Spark is. And its job is to enable native JavaScript support in Spark. And we'll see why that's needed when we look at some source code. And why are we doing this? Well, again, we believe a lot of companies are moving to Node. And we believe those companies will probably have a need to use some sort of big data analytics system out there at some point. But right now, it's really hard for them because they have to do some sort of foreign language like Java or Python into their Node environment. And most companies don't want to do that. So again, by bringing, with EclairJS, you can bring big data closer to the application developer because it's all written in Node. It's all 100% JavaScript, and we allow you to kind of reduce the barrier to entry. Also, Apache Spark workloads are really long running. They can be hours, days, weeks. And Node is inherently asynchronous. As a Node developer, you're used to running with promises, with callbacks, etc. So you're used to working with asynchronous code, and that's really important when dealing with these long-running workloads. Okay, so this is going to kind of a quick overview of kind of how this whole thing looks like. You've got your Node application. It's got our NPM module in it. We have this kind of server piece that sits where Spark is. You communicate with that. It communicates with the master. The master then talks to the worker machines. The workers all have these processes where the data is being handled. Okay, so let's look at a really basic example of how to do this, or how to use EclairJS. Of course, you're requiring, this look good? Okay, yeah. To require EclairJS, obviously, pretty standard. And every time you new up this EclairJS object, you get a kind of standalone Spark process you can work with. And one of the first things you got to do is you got to tell it where your master is. So you create a Spark context. That's how it works in Spark. And you tell it where your master is located. In this case, we're going to use local mode. This could be an IP address of your master machine as well. We give it a name that shows up on the Spark job tracker if you want to look at how your process is running. So now we've got to ingest some data into our system. So we can ingest a very simple array of a couple of numbers here. The parallelize method, as the name implies, will take the data and parallelize it among the multiple worker machines you have. And that then returns a dataset object. So this dataset object is think of it as a proxy to your data, because the data could be stored among multiple machines somewhere in your cloud or your cluster. But you can call these methods on your data using this dataset object, and you don't have to worry about where the data is stored. Spark will kind of handle that for you. So once we have our dataset object, we can start running these operations to manipulate the data. I'm sure you're familiar with map functions from JavaScript arrays. Well, the Spark API has a very similar map operation. You give an anonymous function. That function gets applied against all data in your cluster and generates a new data set. In this case, we can just double the values in our data set. We create an anonymous function, we get a number in, we just multiply it by 2, and we're done. What's important here is that this anonymous function doesn't actually get executed in Node. This actually has to get executed in Spark on the worker nodes, because that's where the data is located. So that's why we have this kind of server piece that we have to provide. Because we have to enhance Spark to understand JavaScript, to be able to execute JavaScript and execute this anonymous function against data that it has stored in its systems. And we take care of converting everything, from Java to JavaScript and whatever we have to do to get the magic to work. So you're getting a pure JavaScript number back here, and you're returning a pure JavaScript number out. And we take care of all the conversions for you. Another thing to note is that Spark is based around lazy execution. So parallelize and map actually are no-ops, really. Spark doesn't start things until you actually retrieve data using certain actions. And this is done so it can optimize things for you. You keep certain data clumped together on one machine and so forth. So collect is one of those actions that actually retrieves data, and this is when we actually start doing actual data processing. And being good citizens of Node, we don't want to block ever. So collect will return a node promise. And once the promise resolves, we get this results array back, and we can stop the context and just console log out the results. Let's hope this works. I'll quickly run this just for a. Where's this other one? No. I guess let me try to make this bigger. So this is a very simple example. I'm running here local mode all on this machine. Java is kind of slow to start up sometimes, so you'll see it takes a little bit for it to get started here. Node doesn't have that problem, luckily. But, so Spark is starting up, and eventually we get our results array with our values in them. Cool. So this was, again, very simple code, but this scales, right? If you have like huge amount of data and hundreds of machines, the code will look exactly the same. So let's take a look at a slightly more complicated example. Yeah, this looks pretty good. So word count, which is a kind of a classical example in distributed computing. How do I do a word count if all my data is distributed among multiple machines? So I skipped a couple of lines here to do the requires and all that stuff to keep it more readable. So of course, the first thing you do is you read in your text file. There's a nice little text file method that does it for you. And we have this data set that has every row stored in that text file. So we got to split this out right from lines to words. And we can use something like a flat map here to do that. So again, we have an anonymous function. We have a line, which is a string. And we'll be naive here and say, let's just split by space. We won't worry about punctuation or anything like that. And this will, again, create us a new data set that's just all the words in the file. So if the word node appeared 10 times in this file, we'll have 10 entries in our data set that contain the word node in it. To continue, we'll talk a little bit about how Spark actually stores its data. So every item in our data set is actually called a tuple. Tuples are just a list of values of any type. So far, we've had tuples of length 1. They can be of any length. And tuples of length 2 are called pairs. And those are special because they're treated as key value pairs. And by having a key, you can actually optimize certain operations. By having them grouped together, again, in the cluster and so forth, Spark can optimize things for you. And there's a bunch of operators, like reduce by key, which you can see, which only works on pairs, and which is what we want to, which we need to use. So again, the first thing we have to do is create the pair. We again we use the map to pair function. We give an anonymous function. We get a word in. Just don't worry where this tuple2 class comes from right now. And we can just return this new tuple2, and the word being the key, and the 1 being the value, because it's a singular count for that word. Now we have a data set that has multiple pairs in it. 10 of them maybe have the word node as the key, and the value of 1. Now we can simply run a reduce function, map reduce. You might have heard of that. It's the classical big data thing. Now we can call this reduce by key and give it a reducer function. It gets applied on 2 items at a time. So we get the value of the first item, the value of the second item, and we expect it to return a new value for those 2 items reduced. In this case, well, we're doing a word count, so we just want to add up those counts. And this gives us our reduced word count, actually. And by having, again, everything keyed, Spark can optimize things for us and do this in a relatively efficient manner. And then again, we can collect and write it out. Let's quickly just execute that. And again, the similar thing is if you want to sort your data, you can do a sort by key. And then the key is just the value that it will be sorted for you. In fact, this example will do it once it finishes. It also takes longer when I demo. It's hilarious. Okay, eventually it finishes. And this case, the file, and I don't know if you can read this, but there were 35 occurrences of the word of, 30 occurrences of the word the, and etc. So this may seem kind of weird because we're just doing a word count on a text file. But the idea is that this code would be the same even if you had like gigabytes worth of files you were trying to process. The code would not change in any fashion other than probably the way you read the data in. And this is a technical aside for people interested in JavaScript. One of the fun issues you have with JavaScript and remote execution is that what if my anonymous function, like this function here, I can highlight, oh wait, sorry. This function here with a tuple 2, there's no way in JavaScript to take this anonymous function and have somehow compile out a new version that has all external dependencies built into it. Any variables I reference in this anonymous function, there's no real way of getting them all built in into some new thing that I can execute remotely. It's one of the kind of trade-offs when you have scripting languages in remote execution. Right? If I want to use some value that I've pre-computed before this function, there's no real way in Node or any JavaScript engine just convert that into something new that has all that included. So we had to solve that in a weird way, having this, come on mouse, this array object here. And this is basically an array of values that you need available for this anonymous function. And basically all your dependencies have to be listed here. We make sure that gets sent over, that we can then add them as arguments to your anonymous function. This is how this tuple2 class magically appears. And this is kind of similar to the bind or apply methods you can use on functions in JavaScript. If somebody knows of a better solution to do something like that, please do tell me, because our biggest issue is dealing with this kind of stuff. That's a quick technical aside of kind of the fun issues you run into dealing with JavaScript and remote execution, or any scripting language, really. OK, so now we can look at an actual full-size demo. This is, we have a bunch of these. Our source code for these is open source. And hopefully this will run. It's finicky. OK, where is Safari? Okay, the resolution is kind of weird in this machine. OK. So over here is a basic demo, demoing a sales of one item in one store. This is based on actual real data from an actual retailer in the United States. It's modeled after real data. So what we have here on the right side is we're simulating the sales of the product over a day. We're accelerating it for demo purposes. This is a kind of a cumulative bar chart. So you can see, the sales go during the day. We chart them, and at the end of the day, we then chart the actual sales in this orange line graph on the left. Concurrently, we're also doing some predictions here using machine learning. So the blue line is actually our prediction engine, trying to predict the sales for a given day. The predictions here aren't the greatest because I'm running this on this one machine, and we have to use only a year's worth of data, else this machine sounds like a jet engine. So the predictions aren't the greatest, but the graph kind of follows the same shape and form. So what you have here is actually two Spark features. You have streaming, so we're streaming in data, sales, a sale at a time. We're streaming it in, doing some mathematical computations, some bucketization, and we're doing machine learning at the same time. The machine learning stuff is actually kind of interesting. We use, again, a year's worth of data. And then every date is basically transcribed to certain data points that are then mapped in this machine learning algorithm. So it's by date only. So it's like, is it a Monday, a Tuesday, is it a weekday, is it a work day, is it a vacation day, is it a holiday, is it Black Friday, is it Christmas, et cetera. All these kind of data points that it can use to kind of describe a day. And then it tries to match that data to the day you're trying to predict. The interesting aspect of this demo is how would you improve that? What data could you add to this kind of system? You can do weather APIs for certain sales, right? Certain products sell better when it's hotter, colder, and so forth. And even though you probably can't tell, we're using New York here as a map. And the reason is New York actually has open API for all its street closures and events. And that's another thing that can actually be used to predict the sales volumes. If there's a street festival happening down the street, well, your soft drink sales may go up, or something like that. So this is kind of a basic demo, just kind of showing off kind of how to run everything. And this code is all just using an Express app and some D3 and some Google Maps, and the source code and data is all free if you want to use it and try it out. It's actually not bad, the predictions right here. Because yeah, we have GitHub repository with all these examples if you want to look at them. How am I on time? Okay. So quick product status, we support the latest version of Spark, which is Spark 2.0. We have support for the older version, which was 1.6. On the performance side of things, we are currently still slower than Java. So Java, same code being written in Java or Node. But we are actually faster than certain other languages like Python. There's no like concrete benchmark really that we can just point at and say we're 20% faster or whatever. But so far, everything we've run, we've been faster. And we're still working on performance, because of course performance is pretty important when you deal with kind of massive amounts of data. We have a relatively new repository. We used to have 2 repositories, one for the client, one for the server. That confused a lot of people. So pro tip, reduce the amount of repositories you have in your projects. We also have a bunch of examples if you're interested for like machine learning, for SQL, for streaming built into a repository. In fact, we have all the machine learning examples that Spark ships with convert over to Node. We do not support the distributed graph engine called GraphX for technical reasons. Only Java can access it. It's a design flaw in Spark. Also, we know that Spark is a complicated thing to start playing around with. It's Java and then Spark and there's other things you have to install. So we do offer a Docker container that has Spark, our server, all our example data built into it. This allows you to run all our samples, without having to install anything on your system other than Docker. It's a great way to get started if you're interested. In closing, the product is meant to allow Node application developers to work directly with Spark using 100% JavaScript. There is no, all your anonymous functions are JavaScript, all your everything is JavaScript, all the types are JavaScript. We're in open source, we're in active development for a year. We're always looking for contributors as well as use cases. Part of our team is meant to not only create new technology, but also make sure that they're actually useful to people. Try to prove them out in the wild. So we're always interested in hearing about people who are interested and also willing to help with that. So a couple links, we have a website, we're at GitHub, we have a Google group, we have a Slack channel, etc. And thank you very much.